All right, welcome back. So we're going to talk about quickly higher derivative notation here. So the first derivative we can write as f prime of x or dy dx, or this would be command notation. So take the first derivative of whatever you put in these brackets here. But we can actually talk about the second, the third, and the fourth derivative and so on. So what do their notations look like? Well, here you can see f double prime of x, that would be the second derivative of f. Then you have f triple prime of x, then f quadruple prime, and so on and so forth. Now, when you get past four primes, it kind of gets difficult to see how many primes you have. So sometimes you'll see textbooks put little Roman numerals up here, or maybe they'll put numerals like this, like four. All right, it depends on the textbook, quite honestly. But there will be times in this class when we're talking about f prime and f double prime a lot, occasionally even f triple prime. All right, if we're using the dy dx notation, Leibniz notation, it's very similar, right? Only look at what we do here. We write d superscript 2y dx superscript 2. We don't really read them as squares or exponents. So I would prefer we read this as the second derivative of y with respect to x, but this is how you do the symbol. If it's the third derivative, you put the 3 there. If it's the fourth derivative, you put the 4 there. If it's the 100th derivative, you have 100 there. And you can see command notation follows a very similar suit. All right. So this video is all about just how to get the first and the second derivative. Now, we already know how to get the first derivative, right? So if this is my y right here, all right, if this is my y, and I want to go ahead and find the derivative, then I'm going to use the rules that we learned. So we learned a couple of rules, and that was that the derivative of a sum is the sum of the derivatives, derivative of difference of the derivatives. So I'm essentially going to take the derivative of each one of these terms individually, right? I also know the power rule, right, for derivatives, and I also know constant multiple rule, right? So if I go to take the derivative of this, and maybe I'll take my time for the first one, you have the constant, and now the derivative of x to the fifth would be 5x to the fourth. That's me using the power rule. Then constant, the derivative of x cubed is 3x squared. That's me using the power rule, right? Then constant, right? And the derivative of x squared, that's going to be 2x to the 1 using the power rule. And if you remember the derivative here, I could do the power rule, right, and do 1x to the 0, but we could just remember that the derivative of ax is just a. So the derivative of negative 11x is just minus 11. And then, of course, the derivative of 5 is 0. All right. I wouldn't show that step. I really wouldn't want you to show that step. There's no reason why you can't get the first derivative by first doing, all right, 5 times 3, all right, that's 15x to the fourth minus 6x squared plus 16x to the 1 minus 11. Okay. And that is your first derivative. Now, we have meaning for this. We know that this is the instantaneous rate of change producing machine for the graph of y. We also know graphically it's the slope producing machine. It'll get me the slope of the tangent line on the graph of y at any point x. Awesome. So now how do I get this? How do I find the second derivative? Well, you probably guessed it. To get the second derivative, you simply take the first derivative of the first derivative. So in other words, just take the derivative of the derivative. And I'm going to do it the same way. It's a polynomial, so the power rule is still going to apply here. So I'm going to get 60x cubed, I won't show as much work this time, minus 12x to the 1 plus 16. And this represents my second derivative. We will go into what the second derivative tells us and the meaning we can get from it. But for now, I just want you to know how to find it, which is basically just take the derivative of the derivative. If I wanted the third derivative, right, I didn't ask for it, but I could do it. Maybe I'll do it just for kicks and giggles here. The third derivative is simply going to be take the derivative again. So it'd be 180x squared minus 12, right? If I wanted the fourth derivative, it would just be, let's see, that's going to be what? 360x to the 1 minus 0. If I wanted the fifth derivative, right, that would just be 360. And if I wanted the sixth derivative, and really the sixth derivative and on, what would they all be, right? Well, derivative constant is 0. So that's actually kind of an interesting little thing to make a note of, that if you are dealing with a polynomial, right, if you keep taking the derivative, eventually you're going to get 0, okay? All right, so I don't want to go too far off the beaten path. Let's do one more problem where we just find the first and the second derivative. So sometimes before you take the derivatives of functions, guys, you're going to want to rewrite the expression of y just to make your life easier. And not that it's necessary in this one, but we'll just kind of like model the practice. So I'm going to rewrite y. So notice I'm writing y equals here, not dy dx. And I'm going to rewrite radical x as x to the half. Now, you don't have to do that because if you remember, I told you to memorize that the derivative of radical x was 1 over 2 radical x. But if I'm going to be asked to take multiple derivatives of it, then maybe it's better off if I just do it in the power form, okay? This is good to go, minus 2x to the negative 3. This term is good to go. I would rewrite this as minus a half x to the 10th and then plus 1/11th x and then plus 2. I probably should have thrown one in there where the x is in the bottom and you had to rewrite it with negative exponents. I didn't. All right, so consider ourselves lucky, I guess. All right, so now I'm going to write dy dx. So notice how I rewrote y and I wrote dy dx. Do not, guys, when you do your work, do not have stuff that looks like this, right? You have to tell me what your functions represent. You cannot have stray functions on your paper. This represents y, write y equals. This is now going to represent dy dx, write dy dx equals. It's super, super important. All right, so here we go. So power rule here, 1/2 times 2, that's 1. So that'd be 1x to the, I'm thinking subtract 2 over 2, so that would be negative a half. 1 over 2 minus 2 over 2 is negative 1 over 2. Then minus 3 times minus 2 is plus 6x. Subtract 1, that gets me to negative 4. Negative 2 times 8, that's minus 16x. Subtract 1, negative 3. 10 times a half, that's 5x. Subtract 1, that's 9. 1/11th x, the derivative of that is just 1/11th. And then derivative of 2 is just 0. So there's my first derivative. There's my slope producing machine for the graph of y. So now it asked for the second derivative of y with respect to x, which we don't even know what that means right now, but we know how to get it. It's pretty easy. Just take the derivative of the derivative. So that would be negative 1/2 x, subtract 2 over 2 from that. The negative 1 over 2 minus 2 over 2 is negative 3 over 2. Negative 4 times 6 minus 24x, subtract 1 to the negative 5. Negative 3 times negative 16, that's positive 48x, subtract 1, negative 4, right? 9 times negative 5, that's minus 45x, subtract 1, and then plus the derivative of 1/11th, well, that's just plus 0. So that would be your second derivative. Okay, so that's just a little bit of notation practice and how to get higher derivatives other than the first derivative. We will in future lessons actually discuss what they actually tell us, which is pretty neat stuff.